Today we'd like to go a little farther with our speed of wave idea. We've already learned that there are two types of waves, transverse and longitudinal. With the transverse wave, the particles vibrate at a right angle to the energy. The energy is going horizontal, the particles are going vertical. Longitudinal waves, the vibrations are parallel to the direction of energy. So both the energy and the vibrations are horizontal. Yesterday we talked about waves on a string, and we got a formula that predicted the speed of the wave traveling through a string like on a guitar. It depends on tension, and it depended on linear density. We saw that battle ropes have slow speeds for the waves because they are very dense and they are very low tension. So we can easily see the wave traveling down the rope. Then we have things like the guitar string, where the waves travel really quick because the strings are light and the tension is high. Today we want to talk sound waves. Sound waves, just like all other waves, start by a vibration. So it could be something like a tuning fork vibrating, and as it vibrates, it produces sound waves. What the sound waves are a series of compressions and then spread aparts for the air. So this represents the air particles being compressed and spread apart. The source of that compression is the speaker. As it moves forward, it compresses the air, and when it moves back, it spreads the air apart. These compressions spread out over time via chain reaction. They travel from the source to the observer. These are longitudinal waves. These are longitudinal pressure waves, high pressure and low pressure as the speaker moves back and forth. So high pressure where we compress, low pressure when the speaker moves back and spreads the air apart. Okay? So you get high pressure, low pressure, normal atmospheric pressure. Today we want to talk about how quickly do these pressure waves travel. And if you've ever watched things like fireworks or lightning, you know that sound compared to light is very slow. Sound obviously travels quickly, but nowhere near as quickly as light. So when lightning strikes, it's going to take time for the sound to reach us. The light is going to reach us almost instantaneously. Not so with the sound. Unless the lightning happens to strike right next to us like it does in this video. Most times the lightning is far enough off that it takes time for the thunder to reach us. Here is a live map that you can find on the internet. It will show lightning strikes around the world. I happen to find some lightning right near Lawrence, Kansas. Here is a lightning strike, and you can see a circle showing where the sound wave has reached, where the thunder has reached. I'd like you to look right below the L, because there's about to be another lightning strike. And when the lightning does strike, you can see the sound wave spreading outward. This is real time. You can see how painfully slow sound is compared to light. Anywhere on this map, you would have seen the lightning strike almost instantaneously. The sound wave takes much longer. So if you were on a beach by this lake, it might be 10-15 seconds before you hear the thunder. The longer it is between when you see it and when you hear it, the farther away the lightning strike was. If you had been right next to the spot where the lightning struck, you would have heard it almost instantaneously. Okay, so this chart, I hope you all have your reference materials, but you should be able to find this chart. It shows you the speed that sound travels through different materials, and you'll see that sound travels quickest in things that are solid, where the particles are very close together and there's a lot of tension in that material. So that when the sound wave moves, it can transfer from particle to particle really quickly. You'll notice that things like gases, the sound travels much slower. The particles are farther apart. it's going to take longer for the energy to go from place to place through a gas. The most important gas is probably air, and you'll notice it gives you a speed of sound in air of 331.5 meters per second. Realize that that is only true under certain conditions. All air is not created equal, and there are three main factors that can affect it. The number one factor being the temperature of the air. Depending on the temperature of the air, determines how quickly sound will travel. So you take the temperature in Celsius, you multiply by 0.6, you add 331.5 to it, and that will give you the speed of sound through air. Realize that pressure and humidity also make a difference, but they are minor compared to temperature. So the only factor you need to worry about is the air temperature. The other thing I'd like you to be aware of is that sound cannot travel in outer space. The reason is there are no air particles in outer space. So even though you might have a vibrating speaker, there is nothing for it to push on or to pull away from to create the high and low pressure that we call sound. This is a quick video clip from the movie 2001: A Space Odyssey. And you will hear noise in the movie until he exposes himself to the vacuum of space. During this scene, there is no noise. And when the hatch closes and lets air back in, once again we can have sounds take place. Sounds cannot happen if there are no particles to carry the energy. Finally, I'd like you guys to see how you're going to do a math problem with this. So here is a video of some Army Rangers destroying a water tower for practice. And what we want to do is try and figure out how far we are from this explosion. So when you watch the explosion, you'll see it, and later you'll hear it. Okay, so it's a two-step process of what you want to do. You want to get the speed of sound using our new formula. Plug in your temperature, make sure your temperature is in Celsius. Once you get your speed, sound travels at a constant speed, so you put that in here. And then if you know the time, you put that in here and solve for distance. If you know the distance, you plug that in and figure out how much time it will take the sound to reach you. Okay, so we have a bunch of new ideas I'd like you to master. I'm going to give you a whole bunch of problems with this, but not today. We'll do those tomorrow. Okay, so today I mainly want you to get your notes done, send me a copy of your notes, answer a few questions on a Google form, and then tomorrow we'll worry about